Well, I wanted to do a solutions video for the latest chapter homework. There was one problem in particular that I've talked about before, and I want to revisit that situation. There were several on the homework where you had an identity to prove, and you proved it by saying the identity was already true, and then you worked on both sides until you got to a statement that was where you had equality or a true statement. There are logical flaws in approaching a problem that way. I know a lot of people do it, especially at a high school level, for example, on trigonometry identities. However, I want you to see what the flaw is in that and not repeat that mistake. I don't want you passing on bad habits to your students or to anyone else that might be in the room. At first glance, this seems like it's a little picky to be doing it this way, but I'm trying to inculcate good habits and also to not make mistakes. Now, the practice of assuming your identity is already true and then working on both sides, that can be a good way to discover a proof, but it is not a proof, as I will show in this video. What I want to do to convince you of that is to take a statement that we know is false and then approach it in the way that some of you are approaching it, where you assume the identity is true and then work it down to a true statement. So if you let me do that, I can prove to you, for example, that 2 is equal to 1. Let me demonstrate. And then I hope that'll, now 2 is not equal to 1. I hope we know that. So I hope that will demonstrate the reason this is not an acceptable method to conduct a proof. Let's do it. If you allow me to assume that 2 equals to 1, then I'll try to take that and work it down to a true statement as follows. Let me introduce some notation. I want to pick a number. Let a be an integer not equal to 0, and let a equal to b. So if we assume that 2 is equal to 1, then I can multiply both sides of that by a, and I'll get the following. 2a equals to a, which is the same as a plus a equals to a, or since, let me just do it in a separate step. Since a and b are the same, that's the same as a plus b equals to b. So I get that equation. And next, let me multiply both sides by the same thing, which is acceptable. I'll multiply both sides here by a minus b. So now I have difference of squares on the left. That's a squared minus b squared, and that's equal to, just distributing the b out, that's ab ba minus b squared. So if I can then add b squared to both sides, so I get a squared equals to ba. And then if I divide both sides by a, and I can do that since a is not 0, so divide both sides by a, that'll give me a squared over a, which is a, and that's equal to ba divided by a, which is b. Oh, that's true. A was equal to b, a is equal to b. Therefore, 2 equals to 1. Again, that's clearly not true. The fact that we assumed that it was true and then proceeded, none of the steps we did there were illegal. The problem is some are not reversible. So that's one of the things you have to watch out for. There are many other proofs where you can assume a false statement. If you allow yourself to work on both sides at the same time, you can reduce to a known equation, but that surely doesn't prove that your mistake at the first was the correct one. So please try to take that into account. This came into play when you had, for example, in problem 1, it came into play several times on this homework, but in that very first problem you had to prove that the difference of the squares of 2 consecutive integers n and n plus 1, if I take the difference of those squares, that it's simply the sum of the two numbers, that it's equal to n plus 1 plus n. Or, if you like, it's equal to 2n plus 1. Well, some of you just assumed that it was. Those two were equal. And if you start operating on both sides, sure enough, you get a true statement in the end. Well, let's do it the way some of you are doing it. If you assume that's true, n plus 1 squared minus n squared equals 2n plus 1, then when you square this out, you get n squared plus 2n plus 1 minus n squared equals 2n plus 1. The n squares cancel here, and you get 2n plus 1 equals 2n plus 1. Therefore, it must be true. Well, if you notice this, it works just as well if you don't assume that. If you just start with the left-hand side and just say, well, the left-hand side is equal to this. Don't assume it's that. And then it's equal to this. Oh, that's the right-hand side. See, this way, you're not working on both sides at the same time. You've transformed the left-hand side into the right-hand side in a very legal way. I hope I've made the point here, and that you will shy away from that and teach your students or whomever you're dealing with likewise.